for the introduction. Let's see if I can just find my Zoom. It was out before the try to get started. I will share my screen. And in the meantime, I would of course tell you that our department is called the Clinical Engineering, just to have a different name. So I suppose you can see my screen now. Imagedata at Python library. Why would I like to waste your time talking about the Python library? Mostly because I've been working on this for some years. It came out of a need in a project, and I had to find a way of handling image data. So I would like to say something then about this library that is now available to use for anybody. I'll say something about why it came about, when could it be used, and then I will also waste some of the time on the details, including a demo if it's still working. But always interesting to see if the technology is there. Motivation, yeah, good. This came out of a need to do analysis pipelines, including several different programs. It started out with a kidney project, and we had to do like drawing regions of interest in images, and we had to do some image registration to correct for respiratory motion. And we found that we had to use different tools for this. For instance, there was a program called ITK Snap that is good for tracing regions in an image. There are some other programs, for instance, in FSL tools that will do image registration. And they all, at least at the time, used different data formats for input and output. So in order to be able to use these different tools in a clinical setting, at least, we need to convert images from what we produce at the scanner into what is accepted by these different tools. And then in the end, we also wanted to have these images back in a clinical setting. And so converting between different formats like Python, ITK, which has a meta image, and Nifty. I suppose some of you have heard about this data format, Nifty. There are also MATLAB files that are useful sometimes. How do you convert between these and back to Python, including information like patient name, geometry, for instance? It turned out not to be so easy. Python in particular has this problem that you get slice by slice by slice, and you have to sort these slices into volumes, into like a dynamic acquisition, if it's the time-dependent acquisition, etc. How do you sort all these slices into something useful? And then there is, of course, patient information, which is important if this is in the clinical setting. If you're going to bring your results back into the clinical setting, then we need to attach this to the correct patient and study. And then as time passed by, it turned out that this could also be useful for program development in Python. Python, that's, I can't explain why Python just came about at the time. But Python is the basis for this, and it turned out that you could also use this library then to load images into your own Python programs, which you could then build further on. So it could be used also in software development then. So what's an image? We are mostly concerned about digital images because Entry is now taking a picture and it will turn out to be a digital image. Most probably it's a 2D image. It has just X and Y coordinates or something like that. So it's consisting of picture elements or pixels. In medical imaging, we also do 3D imaging, taking volume data. So it's volume elements or voxels. And all these pixels or voxels could then be organized in some n-dimensional matrix. When it comes to medical images, then we are concerned about patients, physics studies, which is a different world in some way, but we have to connect these two things. And one standard way to do this is in the form of DICOM images. Digital imaging and communications in medicine were standardized first in 1993. And basically, it's the information is then grouped into 4 different levels. So from the patient, including patient ID, birth date, etc. The study part, which is like the date you do for exam. Then each study can contain several imaging series. And each series, again, might consist of several instances or images. So that's DICOM in short. And then we have the different image formats. Of course, you have JPEG and TIFF and whatever you would use in the internet or in your publication. But in medical imaging, we are mostly concerned with either DICOM, MIFT, or IPK. MIFT, as it says, neuroimaging, is very much used in neuroimaging world. ITK and also has been around for many years, and I have also some data formats called the meta image, or the more general meta IO is at the moment. And so these 3 formats are the problem. How do you convert something between these 3 different formats? So we needed a way to convert images from the clinical images in DICOM to either ITK or MIFT or to MATLAB and back. So that's maybe the most, that's what we started out with. And then, of course, we can never stop the project. We always find new ways of improving it, adding stuff, like loading files from a zip file and not just from a folder of images. Or you could load them from a server, either a DICOM server, which is a PATS system, or for instance, XNOT, which we are using at the moment. And then also being able to return process data back to, for instance, the DICOM server. And then it turned out it would be also nice to be able to see the images. This is not a visualization project, but it is nice to be able to just show the images once you're doing something. And so the basic command or object there is a series object. You could import this from Imagedata series, and this series object is then build something from some source. It could be a folder on the disk, or it could be somewhere out on the server. You could print, see some information there. We'll come back to this in a moment, like the spacing. You want to disturb me? Oh, I'm not talking loud enough. Okay. I have to focus on the bit in the back. Should be working. So my series object is a subclass of the NumPy MD array. So it's an n-dimensional array, and the series object is then building on top of this. So it has a data format for storing the most important information that is not part of the MMIV array, like patient name, birth date, service name, service description, etc. And it's also building on top of a number of plugins for handling DICOM images, IPK images, NICT images, and also different archiving systems, like just paying files in a file system, or you could run all your files in a zip file. And it's possible to add some transport plugins like HTTP or DICOM or XNAP. Somehow you can't see what it says. Oh, perfect. One thing that comes to mind is how do you address your arrays? In MATLAB, which was written in Porta some very long time ago, they are addressing matrices in column major order, like X, Y, and Z. In Python, which is written in C, it's opposite. And how do you handle this? Well, you just have to handle it and say that the most efficient way to use the memory of your computer is to follow what your programming language forces you into, more or less. So when you in MATLAB address volume like column, row, and slice, then in Python it would be opposite. That's how you have to think about it. So it's C, Y, and X. Or maybe it's not C, Y, and X, because what is X, Y, and Z? You're thinking of a coordinate system, X, Y, and Z. Relating to what? And DICOM is typically the scanner coordinate system. In NICT, it's more like a patient-centric coordinate system. But when you have the images, so like a matrix, it's more like you have rows and columns in the images. And I think that is how you should think of these images, because these images might be rotated relative to the scanner coordinate system. So what is row? Is it actually the X direction, or is it the Z direction, or is it some rotated direction? It is something you might have to think about. And I will skip this once, but you can read from local files, from zip files, from an XNAP server. You can write or send images to a DICOM server just by giving the server name and application entity IP. In some cases, you can also read from a DICOM server if that server supports this. So you have all these slices, and you need to sort them according to slice position or something, according to time. So this service will then create all the slices in a folder called DICOM time and sort this according to acquisition time. Or it could be according to the diffusion p-value, according to the MR flip angle or echo time. These are the ones that I had to define because I had a need. And I'm sure you have a different need. So you could also make your own sorting, like inversion time. So you can define that TI is your new sorting way, and this TI is then coupled to inversion time in the DICOM header. So in principle, you could sort on anything. I'm sure you can come up with corner bases, which I cannot sort. In particular, if you have to combine different attributes in the DICOM header to sort. So, demo. No, perfect. So, somewhere I had a demo. It's not this one, not this one. Yeah. Yeah. So, in principle, you import the service object and maybe a few more And then we can then load a series like this. So it's variable core. So it's goes to a coronal image to see how it can be printed. So it says it's an anonymous phantom image taken on this date and time, and it's series number 5. It has a shape of 3 slices, 320 by 210 pixels. The data type is unsigned figure 16, so it's a 2-byte image typically for Wacom images. And we then, of course, also print this again. One of the interesting properties of this is that you can also see the axis. In this case, there are 3 axes. The first one is the slice. There are 3 slices. And the second case, the second axis is the row and then the column. And then it was also nice to have possibility to see the image like this one. Here in the notebook, I cannot interact with this image, so there is just a middle slice, just to see what is there. Then you can see my famous T1 phantom. Because series is built on top of NumPy, you could also use some of these NumPy methods like the min and max in the example here. So you can use many of those methods that are already present in the NumPy package. It came about that it would be nice to also have color images in some cases. You can make then a color image and then draw both the color image and the grayscale image. Not useful or not so useful, but it's up to you because it's something that you have to build.
Can you do on color payments?
So there's a question from Arvid if I can make my own color tables. This color table here in this example is referring to a jet, and this jet is taken from Matplotlib in Python, and there you can make your own color tables first, and then you can name it and use this name here. So you could use any of the Matplotlib color tables in this argument. So in this example, we are making a new image, 3RGB. So it's making a new image, a color image from the grayscale image, and using this jet color table, which you can see in this image. I'm coming back to this, and my time is running quickly. I have an example here where we are loading to have used this T1 phantom, taking images with different flip angles in order to calculate the T1 value in every pixel. So I will load this data from a folder called T1 wide and sort this according to flip angle. And if I look at what I get, then it shows me that the shape of this matrix is now 6 by 12 by the slice size. So there are 6 different flip angles. There are 12 slices. And if I look at the axis, then it will again say that the flip angle axis has flip angles 1, 3, 5, 8, 15, and 30 degrees. And then you can see the 12 slices, 5 millimeter thickness. And the pixel size is 1.8 millimeters. Now, if I just look at one image here, it looks more or less what you already saw in the previous image. So this is just one example. I could of course make a function that will calculate to the T1. We'll skip this one here, and then use it. So it will calculate the O1, which is the inverse of the T1. I can then calculate T1, click it just to have some data that is possible to display. And we can then see the mean and the max of this because it's fit to 2000 milliseconds. Then I can add a new series number and a series description and see that now it says my series is what I set it to, and the series description is T1 map. So this will follow it, this and this back to the unity box. And we could also display this T1 map. There's also a color bar. It's all the numbers are of course totally wrong, but it doesn't matter from a demo. And then in the end, I can save this to a folder in the document format. And so it should be possible then to find this again if I go to, I'm sure this is way too small even for you to see. So if I could then load this, let's go put this there, and then I could then show this using the jet color ID like this. And by clicking the mouse over, you can see the intensity right in the right corner, and also X and Y coordinates. And you can see there are different values. And it's, of course, possible still to change the window level like we are used to in a grayscale image. To be able to see something like this. Okay. Back to my first presentation here. Scanning quickly. So I have to skip the slicing, but we could slice the images, for instance, like this, taking one particular column in the image and present it. And I think I will just skip back to my presentation. It's an open source project in the way that it's available, but it might not be an open source project in the way that there are many contributors. And I think there are some things that should be in place for an open source project. One thing is actually the higher version control that you can follow the history of all the files that you modify over time. And I think Git is the only way you will do this today. I started out with CVS, but it just shows that I've been working on this for 8 years. You need to put the source code somewhere, for instance on GitHub. You need to produce documentation, and you might also want to publish. It's hard to publish these things, but something to think about. And since it's a Python library, you also want to make it available for people to install, and you put it on QPy. And maybe you also need some automatic building of this distribution. But in the end, with a single contributor, it's first it's hard to produce or make all the things that you need, but it's also a project that people don't believe in because there is only one person or if he is run over by the bus, what happens to the project. So how are my details? You can go to read the docs and see the documentation. It's up there. So there is at least a user guide and some things to get you started. You can find the source code in GitHub. And you can install this on your computer. You simply install Imagedata. If it does not work, let me know. It has been tried on Linux, or I'm mostly working on Linux, and it has also been tried on Windows and Mac, but they're not so fond of these systems. But I'm sure you can find cases where this doesn't work, and then let me know at least. So, of course, always more to do. I'm struggling with the S form and Q form matrices in the MIFI format. How do you convert from scanner geometry and diagram to patient geometry and back? And sometimes this doesn't work. Images are flipped on the way, and it could take some more work. Automatic sorting instead of telling the system that this is time dependent or flip angle data, I don't know. Improve the plugin architecture. Python is changing from year to year, and just keeping up with the progress in Python is a big job. DICOM images, as I said, DICOM standard came in 1993, and the DICOM standard in 1996 had the DICOM MR image, and that's what we are still using, doing it. DICOM enhanced MR and DICOM enhanced CT came about in around 2005, but we are still not using it. The problem with the old standard is that the scanner is hiding slice by slice by slice, and you usually end up with 5,000 files. Each of them has a DICOM header, and you have to sort them. In the DICOM enhanced standard, you could save at least the volume in one, or you could save the whole acquisition in one object. So you would just have one header instead of 5,000 headers. It would be much more efficient, but we're not using it. Yeah, one important question. You're sending two images out to speed. And what do you expect? Or what should happen in, of course, related to my library? If you add two images, what should happen? Well, you might expect something like this. We're adding these two. But is this true? Of course, you're making some assumptions. So, like that these two images have the same shape, that they are taken from the same position in the patient. Because I've been talking about geometry here, and we're trying to keep the geometry of the images to tell where are they taken. Are they the same orientation? Maybe one is rotated relative to the other. And are they the same resolution? Is it 1 millimeter plus 2 millimeter slices? How do you add this? What should happen in the library when you add something like this and these assumptions are broken? So my approach then is that you know what we're doing. We are doing this in the stupid way, just adding. You ask for adding, and you will get adding. And it's up to you what is in there. But it could be done otherwise, but it would take some more effort.
You can do the same time as well.
The same time? At the same time. Since this is built on top of MMIV, then you can add an integer and a floating point image, and you will get a floating point image. You could save that to MMIV, you could save that to DICOM, and that would work. So I think I have come to the end of my time, and maybe also to the end of my presentation. So thank you.
Do we have any questions for Kari?
This is the time for asking questions.